All right, so the warm up's up. So um, yeah, we'll discuss it at 5:15. All right, hey guys. So, hopefully this was, pretty straightforward. It's just meant to be kind of a routine practice with the mean value theorem and what it states. So, for the first one, if you look at the statement of the mean value theorem, right? So let's see. Right. The statement for the mean value theorem, the hypotheses are just that the function needs to be continuous on the closed interval and differentiable on the open interval, right? And this is clearly just continuous and differentiable everywhere. So we should expect the mean value theorem to hold, right? So in this case, f of b minus f of a over b minus a is 4 minus 1 over 2 minus negative 1. So that should be just 1, right? So, and f prime of x is 2x. So take x equals 1/2, for example, right? Yeah. So that's an example of a value where f prime achieves the average slope, right? Okay, so let's look at the next one.
In
so
computational cases like this, we can just take it like have a function as a derivative, right? We don't have to do that whole point by point kind of thing. Yeah.
What
Just
exactly do you mean?
You can treat the derivative as like a whole function. As like
yeah. I mean, for a function like x squared, because it's like simple enough,
okay.
that yeah. In this case, I would say like if you were doing this problem, you can say like without too much, without really any justification. I mean, you can probably just say f prime of x is 2x for all x and r. Yeah, for if f of x is x squared. Yeah.
Okay.
Yeah. So the whole stuff about like, the definition, like by definition, differentiation is something that occurs at a single point, right? The only reason I really emphasize that is just because it matters in cases where the functions involved are like more complicated or exotic, or they exhibit some strange behavior where it's like not really obvious what the derivative should be, or you're just doing any kind of like complicated calculation. That's when you want to make sure that you don't like rely on this mental model of differentiation too much as like a crutch. It's better to think about it like as a pointwise operation in that context. But yeah, for this, like you can definitely just say f prime of x is 2x for all x. Okay, let's see. So absolute value of x. So right. The mean value theorem for absolute value of x on this interval probably fails, right? Because absolute value of x does not satisfy the hypotheses specifically. It's not differentiable, right, at all the points, because it fails to be differentiable at 0. And so if you think about it, right, like the only values that like at the points where it is differentiable, which are all the points except for 0, the derivative is always either like plus or minus 1. So if the average slope here doesn't happen to be plus or minus 1, then you're kind of screwed basically. So this fails. F of b minus f of a over b minus a is 2 minus 1 over 3, so 1/3. But f prime of x equals plus or minus 1 whenever it exists, right? So you can't have And in fact, like as long as the two endpoints of this interval are on either side of 0, like the first one's negative and the second one's positive, then it'll always fail, because the average slope will always be basically between, like, it'll be strictly in between -1 and 1, but it'll never equal either of those two things. So yeah. So absolute value of x is not differentiable at 0. So for this one, 1 over x on 1, 1, 3. This should hold, right? Because 1 over x is continuous on this interval, and it's differentiable on the open interval 1, 3. So, you know, the mean value theorem should definitely hold. So in this case, f of b minus f of a over b minus a is, let's see, 1/3 minus 1 over 3 minus 1, which is negative 2/3 over 2. So this is negative 1/3. And f prime of x is negative 1 over x squared. So take x equals square root of 3. And that should do it. And then lastly, for 1 over x, oops, on -1, 1. Oh, I left a blank slide here. Oh well. This should fail. Actually, hold on. So f of b minus f of a over b minus a. That's just -1, or it's a 1 minus -1. It's just like over 1 minus -1. So this is just 1. And so, oh yeah, but the derivative is always negative, right? So this fails. Like sometimes even for functions that clearly don't satisfy the hypotheses, like the conclusion of the mean value theorem could like randomly hold, I guess, you know, sometimes. But in this case, it doesn't. And yeah, clearly, right. I mean, 1 over x like isn't even defined on this entire interval. Is not actually defined at x equals 0. And it's definitely not continuous or differentiable there. And there's no way to even like extend it. You know, actually, like if we had a function that was just like randomly not defined at a point in the middle of the interval. Oh, actually, no. Yeah, never mind. Okay. Anyway. So, but this clearly, I mean, this is just a completely like insurmountable problem. This like fails in a very severe way. So, yeah. Any questions about this? Any questions, you know, in general about the material so far? Oops. Okay. let's try. Okay. Hmm. Okay, let's try this. So sorry, just looking at a different problem. All right, let's try this one. So let f and g be differentiable on an open interval I, and suppose a, b in I satisfy a less than b, and f of a equals f of b equals 0. Show that f prime of x plus f of x g prime of x equals 0 for some x in a, b. And there's a hint. Consider h of x equals f of x e to the g of x. So yeah, I think it's not actually a particularly tricky problem. So let's say we'll take a little, let's say we'll resume at like 5:35. I'll go ahead and make a room for you guys anyway. Let's see. All right. Okay, so it's not too difficult, especially since they give us this nice hint here. So the solution is, all right, so if we take h of x as suggested in the hint, right, then it's differentiable on, well, yeah, I mean, it's differentiable on I, since, well, it's just by, I don't know, by whatever, the product and the chain rules. And so h prime of x is, well, f prime of x e to the g of x plus f of x g prime of x e to the g of x, right? Again, I mean, that's just by the product and chain rules. I mean, those give you the formula, right? So using the formula, this is what we get. And this is f prime of x plus f of x g prime of x all times e to the g of x. And so if f of a equals f of b equals 0, that tells us that h of a equals h of b equals 0. So there exists some x in AB such that h prime of x equals 0, right? Oh, God. Hold on. Sorry, 1 second. All right. Sorry, my Zoom is like bugging out. All right. Right. So if h prime of x is 0 for this value of x, then that just tells us that f prime of x plus f of x g prime of x equals 0, since e to the g of x is never 0. Right? So there you go. Any questions about that? This one's relatively straightforward. Okay, so here's a slightly more challenging one. So let's see. Okay. Yeah, let's try this. So 9.9. Show ex is less than or equal to e to the x for all x in R. Okay. So let's reconvene in another 10 minutes. Hold on. Yeah. All right. All right. So let's go over this. So the key with a lot of these problems is to like pick the right function that you can then apply some like theorem to and have the result of that theorem be like equivalent to what you're trying to show. So like in this case, given this inequality, if you make the function like, so take f of x equals e to the x minus ex, right? Then we just want to show that f of x is greater than or equal to 0 for all x in R, right? And, you know, you can see that, well, let's look at like f prime of x first. So f prime of x is just e to the x minus e, right? So, well, okay. So what you can say is like, okay, for x greater than 1, f prime of x is positive, right? And for x less than 1, f prime of x is negative, right? So by, what's it? The theorem about increasing and decreasing, yeah, 29.7. F is strictly decreasing on negative infinity 1 and strictly increasing on 1 infinity. So f achieves its minimum at x equals 1, right? And f of 1 is 0. So f of x is greater than or equal to, 0 for all x in R, which is what we were trying to show, right? So remember that like this is ultimately like a corollary of the mean value theorem. So this is corollary 29.7, not like exercise 29.7. No, the corollary from section 29. This is one of the corollaries of the mean value theorem. So we're kind of like implicitly invoking the mean value theorem here, but we kind of already had it bundled up into this nice statement. So are there any questions about that? Okay, yeah, and I guess just to, I won't really pose this as like a problem necessarily, but oh, actually, one thing I wanted to mention, so I was kind of debating giving this as a problem. So exercise 29.3, I think is kind of interesting. So suppose f is differentiable on R and f of 0 equals 0, f of 1 equals f of 2 equals 1. Then show f prime of x equals 1/2 for some x in 0, 2, and show f prime of x equals 1/7 for some x in 0, 2, right? So the first part is kind of trivial, right? Because if you just look at the two endpoints, 0 at x equals 0 and 2, right? So this one is basically, well, not trivial, but it follows directly. So this is direct from the mean value theorem on 0, 2, right? Because the average slope there is actually exactly equal to 1/2. So then the second one, right? How would we prove the second thing here? Does anyone have an idea?
I think like use F1 and F2 and like find some mean value there, and then the mean value in another one, and then somehow come to 1/7 from just finding a whole bunch of mean values
Okay,
of the mean value.
yeah. That's kind of on the right track. Okay, so, but there's actually like a theorem that we have that sort of like does that for us, basically.
Is it the intermediate value theorem for derivatives?
Yeah, exactly. Yeah. So what you can do is like if you could find a place, for example, where f prime is like 0, then every value in between 0 and 1/2 has to be achieved by f prime, right? So like somewhere somewhere between f of 1 and f of 2, right? So Rolle's theorem or the mean value theorem, I mean, they're the same, really. When Rolle's theorem applies, then the mean value theorem always applies. So on 1, 2, right, tells us that there exists an x in, let's say, 1, 2, right? Well, I guess in the closed interval, but right. So then, in the x we found from this part. So if we call this x, so say this is like x1, and then this is like x2. Well, depending on which order, assuming. Right. There exists an x such that f prime of x equals 1/7. That's by the intermediate value theorem for derivatives. Okay. So anyway, any questions about that?
Hi, can I ask a question about the previous question?
Sure. Yeah.
So for the theorem 29.1, it is it said f and g, f is defined on an interval, but here we use like here the f is defined on the whole real number, so we can't apply the 29.1 to in this case.
No, we can, because I mean, well, if f is defined everywhere, then it's definitely, I mean, it's defined on any open interval containing whatever point you're interested in. But I mean, you can also think of R as an open interval itself. So yeah. R is an open interval. So yeah, like 29.1 certainly applies. Yeah.
Yep. So we don't need to invoke this theorem 29.7, but can use 29.1 instead, right?
Well, 29.1 would just tell us that, well, I mean, we know f prime is 0 at x equals 1. But 29.1 doesn't tell us that means it's a minimum, because it could be like a maximum. I mean, it could be like a local extremum. It might not even be, I mean, it could be like an inflection point or something. So yeah, you can't use the converse of 29.1. It sounds like you're trying to use the converse. And the converse just isn't true. So.
Yeah. Thanks.
Yeah. Any other questions? That was a good question. Thank you. Okay. Yeah, so that'll be all for today then.
Thank you.
Yep. Bye-bye.
Thank you.